all that. Don't worry.
About all that. Okay, great. And he's the only presenter today, so give him a good response.
All right. So, in short, we're going to talk about the irreducible representations of this group Mn. Okay. So, we're going to start by just talking about what the group is on its own, and then we're going to talk about the structure of its representations, and then we have 3 rules that we kind of care about for these representations. The first one, just make sure that our representation is well defined. The second one, make sure that our representations are irreducible. And the third one is kind of accounting for any isomorphic representations. And then we're going to look at an example of what these representations can look like. And then I'm going to show you just some brief results. And then we'll talk about some of the stuff we hope to do in the future. Okay. So I'm going to make a quick note about commutativity. We talked about it a little bit last week, but it's kind of important. So commutativity is a quality of an operation where the order you do it in doesn't matter. So if this operation star is commutative, then A star B is equal to B star A. Now groups, though, they don't have commutativity necessarily. So it might be that A times B is X times B times A, and maybe X is not 1, or like the identity which is equivalent to 1. And so if you say 2 elements A and B commute, that means that A times B is equal to B times A. And for this to be true, the operation itself doesn't have to have commutativity. It just means that these 2 elements, the order doesn't matter for those ones specifically. Okay. So the group Mn is defined by some of these are not all the elements, but these are kind of the important ones. So we have n amount of these A's. So we have A1, A2, A3 up to An. And then we have B. And then it's defined by this rule where if you take any of the A's and multiply it to B, and then you switch the order, you get this kind of factor of the next A that comes out. So the A's and B do not commute. And so this is the only time where 2 elements don't commute. So if you take any other 2 pairs in the group, they will commute. And note that this implies that An and B commute, because this wouldn't make sense for An because there's no next element. So that means that An and B commute. We're going to look at M4 specifically. So just there's only going to be 4 A's. And we're going to look at the representation by 4x4 matrices. But really it applies to any prime power matrix or matrices, but we're just going to worry about in 4 dimensions. And so each of the A's is going to be represented with an X with the same index. And then the B is going to be represented with a Y. And again, these are 4x4 matrices. And I want to make the note that there's a concept of cycling about this group that's going to be very important. So I just want to kind of state it right off the bat that it's going to be brought up a few times. And it comes from that relation. And the specific goal of this research is to find all of the possible representations of this group. And they kind of split into different options, and we want to find all those options. Okay. So all we have to start with is this relation where if you take an X matrix and multiply it by Y and then change the order, you get the next one like that. So we have to start with that. So if we take, for example, the case where I is 3, then it would give us x3 times y equals x4 times y times x3. So let's look at what that means. First, I have to say that we start off with the matrix, the entries of the matrix. I is going to have this Greek letter lambda, which is just a variable, and then we use this I and j as an index. So the I represents the matrix we're in, and the j represents the entry we're on. And if we're talking about the first entry, so that's a lambda I1, we just call that a lambda I. Okay. So that'll be a bit clearer when you see what it looks like. So, like I said, we're starting with this equation, and the left-hand side of it is just x3 times y. So this is what x3 looks like, and you can see that it's lambda 3, and then lambda 3, 2, lambda 3, 3, lambda 4, 3, 4. And then this is what our y looks like. So this kind of acts as a cycle. I won't explain too much of how that acts as a cycle, but that's what it does. So if we multiply these two, we get this as a result. Okay, so let's look at the right hand side. So again, this is x4, y, x3, and I won't go again into the multiplication, but this is what we get as a result. And so since these are equal, we know each of the corresponding entries are equal. So for example, that tells us that lambda 3, 4 is equal to lambda 3, 1 times lambda 4, 2, and so on and so forth with each of the corresponding 4 entries. So what we get from that is this equation down here, which tells us that lambda ij is equal to lambda ij minus 1 times lambda I plus 1j. I know that might be a bit hard to see what that means right now, but we'll see how that's useful, and using this equation we can kind of easily build the rest of our representation. So here's what they all actually look like, and we're going to use this equation that we just talked about to kind of construct all this. So if we start from the end, we start with x4, all of these are just going to be the same as the first entry, so that's fine, we start right off with that. And then to go backwards, well, the first one's still just going to be equal to the lambda 3, the first one. And then we use this equation to build the rest. So this entry is equal to the previous entry in the same matrix multiplied by the corresponding entry in the next matrix. So that gives you lambda 3 times lambda 4, and you get this here. And then you continue the same way. So you take, to get this entry, it's the previous entry in the same matrix times the corresponding entry in the next matrix, and you just keep going down like that, and it obviously gets more complicated, but it's the same rule the whole way down. And we have these fifth entries, which aren't really there, but they're going to be important soon. So the way we get those is we still take the previous entry and then multiply to the first entry in the next matrix. So that gives us enough information to build the rest of it, and that's how it's made. And then again, y looks like this. It kind of acts as a cycle. And any representation that looks like this, we call it in standard form. Okay. So let's go over the first rule. We want our representations to hold the same quality as the group about this cyclic nature. So what that means is that as you go down the entries of each matrix, we want to end up back where we started. So that means that each of those fifth entries has to be equal to the first entry in the same matrix. So that'll give us this. Notice that these are all the fifth entries, and these are the first ones. So we need them to all be equal, so that means we kind of complete the loop of the matrix. And we can simplify those to these by dividing the corresponding lambda. And then we also only care about the power of 2 in these exponents. So for example, 6 is 2 times 3. 3 doesn't have anything to do with 2, so we don't care. It's an odd number. We don't want any odd numbers. So we can simplify 4, 6, and 10 to just 4, 2, and 2. So this is our first rule. These three equations have to be true in order for our representation to make sense. Okay. So our second rule is about making sure our representations are irreducible. I'm going to remind us again about what reducible representations are. So the representations that decompose into smaller dimensions. So since we're talking about 4x4 matrices in this context, you can show that any reducible representation is going to break into either 2 dimensions or 1 dimension, like a lower power of 2. So reducible representations of this group are going to look like this, where we have 4 entries, but each of the first pair is the same as the last pair, and that has to be true for all of these matrices. If it looks like this, then it's reducible, and we don't want reducible representations, so we want it to not look like this. Okay. So the way we do that is we compare, in each matrix, we compare the first entry to the third entry, because if those are the same, or well, if it has blocks, then those would have to be the same. So that's what this, it looks like this. So if there were blocks of size 2, then these two would be the same as these two, and that would mean that the first and third entry are equal. So we take out the first and third entry of each matrix, and we want to compare them and try to make them not equal. But we only need one of them to not be equal, because we only need one of the matrices to not have blocks. If one of them didn't have blocks, but all the other ones did, we still couldn't like cut our representation in half because we would have lost. So say like this one doesn't have blocks, but all the other ones do. We can't just take the first two entries of everything because we lost these last two. So what I'm saying is we need to make sure that at least one of them doesn't have blocks, then it's irreducible. Okay, and that's our second rule. We just need one of these to not be true. So the third rule talks about isomorphism of these representations. So using our matrix Y, which again acts like a cycle, we can rotate through the entries in the X matrices and get something that looks different, but we don't want to count it as the same, or we don't want to count it as two different things even though they look different, because they came from the same place anyway. So what that looks like, if we take this matrix just generally X and say it has entries A, B, C, D, then you can do this action with Y and you get D, A, B, C. And so obviously that looks different, but they came from the same place, so we don't want to count them as two different things. Okay. A bit more formally, what we're doing is changing our bases by permuting the basis vectors with Y by conjugation. And I should note, this is the only way to change your bases and still get something that's in standard form. So really it's the only way to change your bases that we care about. If you don't know what all that means, it's okay. We're just talking about cycling the entries. We don't, and again, yeah, we don't want to count two representations that look different as the same if they came from just cycling one into the other. Okay. So if we take our whole representation and cycle them down this way, we'll go from, and again, I'm just using these letters as placeholders. That's what the matrices actually look like, but that's a lot of stuff, right? So I'm just using these letters as kind of a simpler version to look at. So if we cycle all the entries down, we're going to get this, and I want to know that this one is actually the same as up here. There's kind of a technical reason why that's true. I can't really get into it, but basically don't worry about x1. It isn't affected by the cycling, so we're just not going to consider it in this case. So, and again, this x4 has the same entry the whole way down, so cycling it is also not going to do anything. So we really just care about the effect of this cycling on x2 and x3. Okay. So the amount that we've overcounted, like the amount of different looking representations we get, corresponds to the block sizes in x2 and 3, or like the common block size between the two of them. Because if you, well, we'll see an example of what that looks like in a minute. So what we do is we want to adjust our count of options by this amount that we've overcounted. So we want to make sure we're not overcounting anything that just looks different but isn't actually different. So let's look at what this cycling looks like depending on the block size. So this is what we just saw, where say they're all unique entries. So it's B1, 2, 3, and 4, they're all different, and same with X3. Then we'll get 4 options from this cycling, because we could have started on the first, second, third, or fourth entry, and it would have looked different every time. So that's if there's no blocks. And if there is blocks in X2 and 3, so it's like B1, B2, and then just B1 and B2 again, and same thing here, then we're only going to get 2 options from this cycling, because we can either start on the first entry or start on the second. Starting on the third and fourth is going to be the same thing, because as we see here, the second or the first and third are equal, and the second and fourth are equal. So you're only going to get 2 options from cycling something that has 2 blocks, and something that has blocks of size 1. Well, that just means that these matrices are all just the same the whole way down. So you're actually not going to get any new options from doing the cycling. In other words, you get 1 option when they're blocks of size 1, you get 2 options when they're blocks of size 2, and you get 4 options when they're blocks of size 4. So now we can see kind of the correspondence between the block size and the amount we're overcounting by. Okay. So that's all of our rules. The first one is making sure that our representations are well defined and they kind of properly correlate with the group. The second rule is making sure that our representations are irreducible. And the third is kind of adjusting our count by isomorphism, just making sure we're not overcounting it either. And we have these equations for the first rule. So we need all of these to be true, all 3 of these. Again, this checks for blocks in X, or just this checks that X3 cycles back to where it started. this checks that x2 cycles back to where it started, and this checks that x1 cycles back to where it started. And now, the second set of equations is for the second rule, and we just need one of these to be true. And so again, this checks that x3 doesn't have blocks, this checks that x2 doesn't have blocks, and this checks that x1 doesn't have blocks. Okay, so it's kind of a lot, but we're going to look at an example of what these matrices can look like and how the rules work, just to kind of further emphasize what's going on. So I'm going to take the case where lambda 1 equals 1, and then the rest of them are all negative 1. So that's a pretty simple case, and we'll see what that looks like. So, in the first rule, we can see that each of these is satisfied, which means that all of the matrices cycle back to where they started. So that's great. We have at least a representation so far. And in this second rule, we can see that this tells us that x3 actually does have blocks. But if x2 and x1 don't have blocks, we're still good. It's not reducible. So now we have an irreducible representation. And then since x2, this one, did not have any blocks, that means that we would have gotten 4 options from this cycling. So great, we know it's an irreducible representation, and we know the amount of overcounting we would have done. So let's see what that looks like. These are the matrices in that case. So of course x4 is going to have blocks. It always will. And x3, as we predicted, has blocks of size 2, because these two are the same as these two. But then in the remaining matrices, they don't have blocks, because these two are not the same as these two, and the same thing for here. So our equations worked just as we expected. And since all of our rules are satisfied, this is at least one, well, it is just one of the irreducible representations of this group M4. Okay. Again, what the actual point of the research is to actually go backwards this way. We're not starting with options and then looking at the rules. We actually are taking the rules and trying to find all of the options that fit them, which is a harder task to do. But just for the point of explaining it, it's kind of simpler to start with options and then see what happens. Okay. So this is all of the options for M4. I know it's too small to read, but I just want to show that there's a lot. What we did just right now was a subcase of case 2.2 here. But you can see there's quite a bit. And some of them get quite complicated. We picked a pretty simple one, but some of them have a lot more work involved. So, right, this is all of the irreducible representations of M4 with 2 to the n-dimensional matrices. And so we talked about M4 today because it's a little bit simpler, but what I'm doing for my research is M5, which has the same rules and the same kind of structure, but the computations are quite a bit harder. But yeah, we still learned about how M5 works by talking about this because they have the same structure and rules, so it's okay. And M5 has actually never been done before up to now, so it's pretty exciting, and it's quite a bit harder. So, for the future, we're pretty close to finishing M5, but we'd like to finish M5 pretty soon. And we'd like to, once that's done, put the results of M4 and M5 and compare them into a research paper, which we'll hopefully publish this fall. And then in the next year or so, we would like to try, maybe not, to generalize M4 and M5 to just MN. But depending on the results of M5, that may or may not be doable. But what I am going to do is this same work, but for a different group, similar to MN, but not quite the same, maybe 2Bs or something like that. That'll probably be my honors thesis. Okay, that's my research. Thanks very much for listening. I love answering questions.
Chase.
Yep.
This might be a stupid question, I'm not entirely sure.
No problem.
But where does MN come from, and what is the use of MN?
I couldn't tell you. I don't know. It's just, I mean, there is, like I said last week, maybe these groups themselves are kind of what are we doing here? But you can learn a lot about just group theory from seeing the patterns that come out of certain groups. And again, it's a lot of patterns come up that will apply to other things even besides group theory. So I don't know what MN is useful for. I don't really care, to be honest. But I'm sure it's applicable to other groups, and then other groups are applicable to other math and so on.
Okay, thank you.
No problem.
Other questions?
Yeah?
I have a question about, you missed your, the page is about y times x times x, y minus. Could you move the page? One is, first one is the same, second one is not, so why we need to go back? Okay.
Do you mean like here when we compared the two sides?
No, go more. Oh, it's the beginning?
Yeah.
And in the middle, row 3. Row
Okay.
3. Yeah.
Something like this?
And go next page. Yeah, why is first one is C1?
Oh,
C.
do you mean like
Second
why,
one, yeah, next page.
why does this one look the
Yeah,
same?
yeah.
So, I'll give a brief explanation. That's kind of something I couldn't go quite into, but I'll answer. So, it turns out that there are like, for certain groups like this, there's infinitely many representations, but they fall into these kind of like equivalence classes. And the representation where this one looks like, we can scale this matrix by any complex number, and it's in the same equivalence class.
What is the difference between x1 and x2? So a1 and b1 is different, or
Yeah.
have additional property?
So the reason why x1 is different from all the other ones is because in our group relation, when we look at one dimensions, right, we know that complex numbers have to commute. So because of that, we kind of are forced, we force all of the a2s up to an to just be 1 in 1 dimensions, and 2 in 1 dimensions though, we don't know anything about a1. So it's just different because of the group relation basically, and that allows us to scale this one by whatever we want, but we can't scale the other ones. It just comes from the algebra of the group relation, but it's just kind of a bit too much to get into. But so x1 is just different because we're allowed to scale it by any value, where the other ones are forced to just stay as they are.
Can I add
Sure.
something there,
Yeah.
a little more technical? So what's going on is the equivalence classes are formed with tensor products of one-dimensional representations. And so with your one-dimensional representations, you know that most values have to be 1 for commutativity, and the ones that don't can be whatever. So you can scale a few matrices by whatever you want. In fact, x, 1, and y are the ones you can always scale by anything. So you might as well make a 1, 1 all the time.
Okay.
Yeah.
You can always just put it back to where you want it.
Yeah.
Other questions?
I have a question.
Sure.
Why are there so many cases?
Well, it comes from the rules we have. So, like what we did here. Oh, sorry. What we did here was with our example. Sorry, is we picked options first, and then looked at what the behavior is after. But what we're actually doing is taking these and finding all of the options that can satisfy this set of equations. So there's quite a bit when you talk about complex numbers. So like just lambda 4 here. There's 4 options. There's 1, -1, I, and -I that satisfy it. So for all those 4 options, we can get more for this one, and then for that one, we get more here, and just so on and so on. And there's the third rule too. So really, it comes from trying to generalize these equations and find all the options. We just get so many options for how these can be satisfied and in which way they're satisfied. It just kind of blows up. Thank you.
I have one more question.
Yeah.
So, any applications for this representation?
Again, I don't know. It's just, I mean, it is like applicable to other group theory, of course, and then group theory is applicable to other things. But like this specific thing, applicable to other fields of math, I'm not sure. I'm sure there's some way, probably, but I don't know.
Yeah, this is kind of in some sense, the simplest infinite nilpotent group that there is, or the simplest family of infinite nilpotent groups. So it's a good test case to develop techniques. So that's basically what we do.
Okay. Good.
Are there any other questions for Jace? We're really finishing early, guys. Like 12:26. Okay, so let's thank Jace again.